All right, let's jump right into this. We're going to talk about something pretty fascinating today, how researchers are, well, hacking our own gadgets. Not to cause trouble, but to make them way, way safer for all of us.
Just think about it for a second. That smartwatch on your wrist, the big screen in your car, maybe even your coffee maker. They're all powered by these little computers running software that you never, ever see. It's this hidden code that makes our modern world tick.
And that brings up a huge question, doesn't it? If all this code is tucked away, sometimes in just one giant, confusing file, how do we know it's actually secure? Who's looking under the hood to find the problems before the bad guys do?
To really get that, first we've got to understand what this hidden code even is. It's like the invisible brain running inside pretty much every smart thing we own.
It's called firmware. And unlike an app you download, this is the permanent stuff that tells the physical hardware how to be a smartwatch or a car. The real problem, and this is the key, is that it's often monolithic. That just means it's one big blob of code, making it incredibly hard for security researchers to pick apart and analyze.
So, if it's this tough nut to crack, how in the world do we test it? Well, this gets us to the heart of the problem, what we call the firmware fuzzing challenge.
One of the most powerful tools we have for this is a technique called fuzzing. It's pretty cool, actually. You basically have a computer throw mountains of random garbage data at a program, and you're just waiting for it to crash, because if it crashes, boom, you've probably just found a bug, and that bug might be a serious security hole. Now, you can't really do this on your actual smartwatch. It would be insanely slow, just not practical. So the modern solution is something called rehosting. You basically lift the firmware right off the device and run it in a simulated world, an emulator on a super powerful computer, where you can go much, much faster. But here's where it gets really complicated. That firmware is constantly trying to talk to hardware, sensors, buttons, network chips that don't exist in the simulation. It does this using something called memory mapped I/O, or MMIO. Think of it as the special language firmware uses to talk to hardware. If your emulator doesn't speak that language perfectly, the whole thing just grinds to a halt.
And that communication breakdown leads directly to what researchers have dubbed the wasted effort problem. It's honestly the biggest reason why finding bugs in firmware this way has been so painfully inefficient. This quote from the research paper just nails it. The firmware asks the hardware for a big chunk of data, but then it only actually uses a tiny little piece of it. All that extra data is what they call input overhead, and it's a massive, massive waste of time for the fuzzer. Let me show you a real-world example to make this crystal clear. This is a piece of actual firmware code. All it's trying to do is get a single character. But to do that, it has to check a status, flip a light, then read the data. All in all, it's reading 12 or more bytes from different hardware locations, but at the end of the day, only one single byte of that information actually matters to the program.
And this chart shows you how crazy that is. In that one little function, at least 92% of the input the fuzzer has to generate and feed to the program is completely useless. It's just noise, total overhead.
Think of it like this. It's a great analogy. The fuzzer is like a pilot trying to figure out a new plane. But 92% of the switches and dials in the cockpit are completely disconnected. They do nothing. So the fuzzer is spending almost all its time just randomly flipping dead switches, hoping it eventually stumbles on the one or two that actually fly the plane. So this is where the big breakthrough happens. A team of researchers built a system they call FUZZWARE, and it takes a completely new and way smarter approach to solving this exact problem. Here's the core difference. The old way was just blind guessing. The fuzzer threw random numbers at everything and just hoped for the best. FUZZWARE, though, is different. It's intelligent. It actually looks at the firmware's code first to figure out which inputs the program is just going to ignore and, more importantly, which ones it actually cares about. Okay, so how does it work? It's a really slick four-step process. First, the moment the firmware tries to talk to a new piece of hardware, FUZZWARE hits pause. Second, it does this really deep analysis of the code to see exactly how that data is going to be used. Third, based on what it learns, it builds a tiny, super precise model for that interaction that cuts out all the wasted overhead. And finally, it lets the fuzzer go to work using that smart model, focusing all its energy only on the bits that count. It is literally fuzzing smarter, not harder.
And it's really clever about the kinds of models it builds. For instance, if the code is just waiting for one specific number, it makes a constant model. If the code reads a big number but only uses a few bits from it, it builds a bit extract model. It's this level of precision that makes the whole system so powerful.
Okay, so that all sounds great in theory, but does it actually work?
Well, let's take a look at the results, because honestly, they speak for themselves.
The first big metric is code coverage. Basically, how much of the program's code did the fuzzer actually manage to test? Compared to other top-tier tools, FUZZWARE explored up to 3.25 times more code. That means it was reaching deep corners of the firmware that were basically invisible before.
And here's why that happened. By building those smart models, FUZZWARE was able to slash the input space, all those disconnected switches in our cockpit analogy, by up to a whopping 95.5%. That's an incredible amount of wasted effort just gone.
So, more coverage and less waste leads to one thing: finding more bugs, and boy did it. FUZZWARE uncovered 15 brand new, never-before-seen security bugs in firmware that's used all over the place. These weren't trivial either. They led to 12 officially registered security vulnerabilities.
And just to put a cherry on top, it also proved how robust it is. It became the very first automated system to pass 100% of a critical industry benchmark. This thing isn't just a prototype, it's solid and it just works.
So, let's bring this all back to what it means for you. Why should you care? Well, it means safer smart devices in your home. It means better security for things we all rely on, like critical infrastructure. It means we can find and squash these bugs before they become a problem, and that builds more trust in this connected world we all live in.
And that kind of leaves us with this final thought to chew on. Our world, our devices, they're all getting smarter and more complicated by the minute. And what the work on FUZZWARE really proves is that to keep all that stuff safe, our security tools can't just work harder, they have to get a whole lot smarter too.